as I said previously, being well versed in converting from H3O plus into pH and back, and into POH and back, and into OH minus, is helpful for starting many of these chemistry problems associated with acid-base character. Like this one. Given a mass, a volume of HCl that has a solution of pH of 5, how would you make it? How many grams of HCl do you have to put into that 300 mils? So, often our way into acid-base problems is H+, H3O+, because we have ways of measuring it quite readily, and one of them is pH. So H3O+, if we have some way to relate H3O+ to other things in solution, we have a handle. And in this particular case, we do. HCl is a strong acid. Because it is a strong acid, we know that when HCl dissolves in water, it will dissociate fully. That this reaction, HCl plus water, produces H3O plus and Cl minus, such that this is effectively 0, and therefore the concentration of HCl in solution will equal the concentration of H3O plus, the initial concentration. There's actually no, or almost no, undissociated HCl. So when we write these equilibriums, we're assuming that this is not dissociated. Luckily for us, if we know the H3O plus concentration, we get to HCl, and in this case we do because we have the pH. pH is equal to 5.00, and so therefore 10 to the negative pH will equal the H3O plus concentration, which in this case will equal 10 to the negative 5, or 1.0 times 10 to the negative 5th, will equal our, and that's molarity, equal our H3O plus concentration. And it will also equal our HCl concentration, because these two are equal. In a strong acid, all of the acid is released as H3O plus, converted into H3O plus and its counterion. So once we have that concentration, we know that for a 300 ml solution of that, of 300 ml solution of the acid, we know that for every 1,000 mils, that is 1 liter, and we know for every 1 liter of the acid, that is equivalent to the -5th moles of HCl. Again, this is just our molarity statement that we just figured out. And from the molecular weight, 1 mole of HCl, 36.5 grams of HCl. 1.1 times 10 to the -4th grams. So less than a milligram of HCl will drop the pH of water to 5. So quite impressive in its ability to change the pH. So strong acids, it's a very direct relationship. For strong acids, we assume all of the acid dissociates into protons. For every 1 mole of acid, we liberate 1 mole of protons. Therefore, if we know the moles of protons, we know the moles of acid. So there's a small handful of strong acids. Most of the common halo acids and the common polyatomic acids like sulfuric and phosphoric are fairly common. The only thing to remember is that polyatomic ions will liberate only 1 proton. So a 1 molar H2SO4 solution is approximately 1 molar in protons. A 1 molar sulfuric acid solution is approximately 1 molar in protons. All right. Now bases are a little bit different. We have to just be cautious with the bases. The bases are ionic, and so most of the ionic strong bases will liberate one hydroxide, but some of the polyatomic, some of the polyprotic bases like strontium hydroxide and barium hydroxide, they will release two hydroxides. So the molarity is not always 1-to-1. Rely on the stoichiometry. So let's take a look at an example. We're just going to cover one of these examples. So what is the pH of a 6.7 times 10 to the minus 5th molar HClO4 solution? That's perchloric acid. For a strong acid, for the molarity of H3O plus will equal the molarity of the acid itself. Another way of thinking about this is the definition of molarity, moles of HClO4 over liters of HCl4, and we know that for every 1 mole of HClO4, that will release 1 mole of H3O plus as the reaction is consumed. This will then, the units cancel, moles of HCl moles, this leaves us moles over liters, and this leaves us moles of H3O plus over liters, and you see that this is a 1-to-1 relationship, and so therefore these two numbers are equal. And that's the long form. But simply this will equal the H3O plus, and so therefore the pH will equal -1 times the log of 6.7 times 10 to the minus 5th. Or 4.17. And to check it, 10 to the negative 4.17 will equal 6.7 times 10 to the negative 5th. All right, so knowing the pH, you can go to H3O plus. Knowing the H3O plus, you can go to pH. Or knowing the pH, you can go to acid concentration. So what we did here. Base solutions are not much different, except that we use pH, but we're not looking for H3O plus, we're looking for OH minus. So let's talk about this pH 8.15 solution. And they want to know how to make it with barium hydroxide. Again, for every 1 mole of barium hydroxide, that releases 2 moles of hydroxide ion. The pH doesn't have anything to do with hydroxide. pH has to do with hydronium ion. So we can use 10 to the negative pH to give us the hydronium ion. Or, alternately, we can go to OH minus via POH. Y 14 minus pH will equal POH. 5.85 would be the POH. 10 to the negative POH will equal OH minus. This becomes equal to 1.41. 4 times 10 to the minus 6th. That will be a hydroxide ion concentration and molarity. So how would we make a barium hydroxide solution with that concentration using this molarity? Again, we know that it's 1.4 times 10 to the minus 6 molar hydroxide. And we know that for every 2 moles of hydroxide, that is equivalent to 1 mole of barium hydroxide. says that we would need a molarity of barium hydroxide equal to 7.0, 7.1 times 10 to the minus 7th molar to obtain a pH equal to 8. Given one of these values, you should be able to find any of the three other ones, which indirectly tells you about the concentration of acids and bases in solution. Strong acids and strong bases, we can assume a 1-to-1 stoichiometry or 1-to-multiple stoichiometry for polyprotic bases. Right? But the assumption is complete dissociation. That falls apart with weak acids and bases. So if we can't say for sure that it's a strong acid or a strong base, we can't use that assumption.